All right, number 8, intermediate value. In calculus, we call it IVT, intermediate value theorem, IVT. There's an MVT and an EVT and a, okay, anyway. Intermediate value theorem, IVT. Number 10 matches with F. Number 12 matches with E. Number 14 matches with B. Pause. I was catching last homeworks that were due at the end of last week. And there is something that I am having to still take points off on homeworks that I don't want to be anymore. Can you guys check your 10, 12, and 14? Can you check your 10, 12, and 14? Did you guys just put F, E, and B? Or did you sketch the graphs that are supposed to match the equations? What are the directions from me as to how you do homework? Summarize the directions. Someone tell me directions for 10, 12, 14. What'd you write? Perfect. Perfect. Match the graphs. I love it. Jason, thank you. Gracias. Ooh, I get to be Mrs. Regan. I'm on it. Okay. Wasn't she a cell phone Nazi queen? Okay, coming back. So, you were supposed to say match the graph. Good, that's writing the directions, but what else are you supposed to write? The problems. So, the problems. Didn't you have this function, that function? Did you write those down? Some of you would. But did you just write F, E, and B? Sketches along with it, because that way when you come up here and look at the answer key and you get one wrong, you're like, wait, what went wrong? And we can talk about it, as opposed to, oh no, I just guessed the wrong letter. That doesn't help. Okay, you're supposed to have the sketches. I don't like taking points off. I want you guys to get hundreds on these homework checks, and I don't want to have to work so hard either. But it would also help your score. Okay, so make sure you're doing homework correctly. Number 26, if you guys have questions on those, we'll get into the homework in just a second. Number 26, the degree is 5. Leading coefficient is a positive 4. The degree is odd. Leading coefficient is positive. Therefore, oh, come on. That's an elementary description. We're so much better than that, aren't we? How can we describe end behavior even better than, okay, falls to the left and rises to the right? That's good. But how are you supposed to do it? As approaches. Which one is that? Going to the left or going to the right? Going to the left. F of x, how do we say falls? As x goes to negative infinity, f of x goes down. So yeah, negative infinity. And how do we go the other direction? As x goes to positive infinity, f of x goes to, because as I go to the right, up. I'm not going to do this on all of them, but I did tell you yesterday that you weren't just supposed to use this wording. You were supposed to use our notations that we're trying to learn. And I think I referred something to, I'll see which kids just do calc chat and which kids don't. Now, some of you are like, well, I saw the answers in the back, and so I strategically made mine match. Yes, but you have to pay attention in class when I say end behavior or leading coefficient test. I want it written like this, okay? Moving on. Headers and footers, that's awkward. I don't there. Okay. Number 28. Thanks, guys, for hanging. Number 28. Leading coefficient. Nope. So nope. Before that, degree is 4. Leading coefficient is 3/4. What? What? Did anybody just put 3? Why is it? What? Yeah. This technically isn't a polynomial as written. I mean, it is as far as what it means, but it's not as far as the proper form. What's the proper way to rewrite this polynomial? We actually see who is A, who is B, and who is C. Yeah. When you divide by a number, don't you multiply by as reciprocal? So would it technically be 1/4 times 3x to the 4th minus 2x plus 5? What is the leading coefficient? 3. No. 3/4. Right? Technically, the leading coefficient isn't 3. It's 3/4. Degree is even and positive, so whew, got it. But how do we write it in our snazzy notation? I'm not going to write it out. You got to listen. As x goes to, which way am I leaning? Left, so negative infinity. What are y's doing? F of x is approaching. Good. As x is approaching, positive infinity. What are f of x is doing? Positive infinity. Good. So whether you go to the right or to the left, the graph is increasing, aka as x goes to negative and positive infinity, f of x's are both going to positive infinity as well. 36 allows us to do some math. Whew, finally. Factor difference of squares. Got it. Set each equal to 0. Got it. Zeros, plus or minus 9. Gavin, were you acing this last night? Why does each 0 have a multiplicity of 1? That's okay. Who has a name for these guys? Factors, good. Each factor. Good. Each factor, which is where each of the zeros come from, have exponents of 1. So this factor has an exponent of 1, that factor has an exponent of 1. That's why their multiplicities are 1. And do you guys see how in the graph crosses through at each of those zeros with multiplicities of 1? Oh, it doesn't bounce off, though. Oh, yeah, it doesn't bounce off. Yeah, it crosses through. There's only one turning point. That's the maximum, and we can see it as we graph it. Did they let you use your graphing calculator? Spoiled rotten. But wasn't this an easy one anyway? It's a parabola that's been reflected down and then shifted up 81, which I think would have been easier than playing with my window all day long. But maybe some of you knew to make your y max 90 or 100 or something like that to see the 81. Maybe some of you would have done that fast. 76. Do your sufficient, how did the directions say? It was really weird, right? This is for letter C. Sufficient solution points, is that what they said? Yeah. Do yours have to be the exact same as the ones they chose? No. Could they have been? Double check your factoring, double check your zeros. That's where we had to start. They talked about end behavior. It's even. I knew it was going on to the left. It was going up. My job was to kind of figure out the general idea of what's going on in the middle. In case a few of you guys got a little stuck on your sign chart, I would have thought of my zeros. Oops, not positive 4. They're just showing the points. They're not showing the sign chart. They're just showing the points. Remember, our sign chart has the points in there, which is why I like them. Technically, if we wanted to be super precise, we would make 3 columns, or 3 rows, I should say, where we have the intervals first, and then we have our test x, and then we have our f of x. But your intervals should have been negative infinity to negative 3. What was the next interval? Good. What did you guys choose as your test point? Yeah, I think I would have done negative 4, but it's okay if you didn't. That's all right. Just had to be something in there. How about this one? I would have chosen a negative 1. It's easier to plug in, but you could have done negative 2 also like they did. In here, and then in here. So you could have done negative 5, negative 2, 2, 5. I mean, I wouldn't do negative 1.79632. You have to plug that in. Oh, don't do that. Pick a nice number. So did it have to be their points? No. Could have been your own points. But hopefully when you ended up plugging in negative 4, you figured out that he was really high. And then you figured out negative 2 or negative 1-ish was fairly low. Then you had your other 0 fairly low again, your other 0, and then really high. Now, could yours have been a little bit off depending on what you chose? Yeah. But did you get the general idea of the movement and the motion and the zeros? Yeah. And if you wanted a better picture, could you have plugged in negative 1 and negative 1.5 and negative 2 and negative 2.5 and gotten some more points to have a better idea? Yeah, you could have. But it was to get the general idea. Robbie. Oh, remember when we're factoring, you always look to see if there's a GCF? So the GCF I saw right away was the x squared. But an in-between step would have been to pull out the x squared. Remember, when you factor, you divide. So x to the fourth over x squared is another x squared. You can always check by distributing. Good. Minus, divide by x squared. Then you can say, hey, that's a difference of squares, isn't it? X plus 3x minus 3. And remember, when you're finding the zeros, you take that function and you set it equal to 0. Good. And when you set it equal to 0, you set each factor equal to 0. Which one has a multiplicity of 2? The x squared. So at what 0 is my graph going to bounce?
0.
And does it bounce? Yes, it does. Crosses through, and then it bounces, and then it crosses through. If you were like, I think I basically got the idea of 76, like I basically got it right, give me like a one of these or a one of these in the upper quadrant-ish. Okay, that's the majority of the class. Good. But if you guys are getting stuck on this, this is a great like big picture problem of putting a lot of ideas from section 2.2. It's not like the end of chapter 2, but it does get the big idea of 2.2 down in one problem. Does that kind of make sense? Cool. But what would make this problem harder? Can anybody tell what would make this problem harder? Yeah, what if it was x to the fourth plus 4x cubed minus 9x squared plus 11x plus 1? Factor. Go in a corner and cry just a little bit, right? What was true about this factoring? Easy. GCF, difference of squares. Doesn't mean it was like the easiest problem ever. A poor little 8th grader, 9th grader would start crying. Well, they haven't learned factoring yet if they're in Algebra 1. That's why. But coming back. You guys, it should be easy-ish for you as far as factoring. But in section 2.5, we're going to put all of these ideas together with harder polynomials. But we're building up to that. Kyle, go ahead. Oh, we could use, oh, I just got rid of it, didn't I? As x, yeah, let me say it one more time. As x goes to negative infinity, y goes to positive infinity, or f of x goes to positive infinity. And then as x goes to positive infinity to the right, f of x goes to positive infinity also. Is that good? Do you have any more evens? Oh, yep, 94. What theorem was 94 asking you to use? Yeah, but what were you allowed to be using during that problem? Was it all by hand? Yeah, use your calculator, please, please, please. This is one of those, like, let's start crying in a corner type problem, if we had to do it by hand. Zeros or any of that stuff. So they said, these are nasty zeros. Look at the function. Ugh. So instead of using the zero feature right away, they were asking you to make a table, to go by ones and say, hey, about where is the 0? And as I made a table, and as I went by ones, I found a 0 between 0 and 1. But why? Why do I know that for sure, for sure? Because the y's go from? Yeah, had to go through 0. Where's another one? Ooh, between 6 and 7, and then? Between 10 and 11. How could you have made it more precise? Go by 0.1s. More precise, go by 0.01s. More precise, go by 0.001s. And you could have gotten to this without ever feature. You could have gotten to that without ever using that feature. Now here's something crazy. If you ever did, I'm trying to think of how this could practically be useful to you. Sorry guys, I know the air isn't turned on. I know the sun is shining in. Just hang in there. The sun's going to go up and hopefully kick on. Let's say, I'm not sure I can make this applicable to you guys, like as far as you seeing a direct application where it will be helpful to you until we get to section 2.5. So let's hold off on the practical application, but just in the back of your minds, remember the IVT can help you narrow down zeros if you are not quite sure where it lands, even if you have to do the problem by hand without a calculator. But we'll come back to that. Just remember, when problems get messy, when they get nasty, maybe not this bad, you won't ever have to factor something like that by hand. Maybe not this bad, but when the problems get messier, the polynomials get longer, IVT will be a useful tool. But we'll come back to that when that happens, okay? For right now, we're done with the evens. Let me go back to the homework problems up here so I can hear from you. Any evens or odds that you want to talk about or talk through? Tony. 45? And what was the second one? 45 and...
45A.
Oh, 45A. Gavin, what do you got? Anything else? Sam. Which one? B. And then Robbie? 45. Do you have like a particular letter or just kind of the whole thing? So let's go ahead and start with number 45, work our way up to, oh, okay. So for sure, A and B. Okay, so then, thanks, Kim, for getting my attention. Number 45 is our first problem, and I think it's on the second page. Does that sound right? Okay. Number 45. We have t to the fifth minus 6t cubed plus 9t. Does it have a GCF, yes or no?
Yes.
Oh, okay, well that's good. But what happens even after you take out the GCF? Is it a quadratic? Isn't it a quartic?
Yeah.
Okay, need to remind myself in my head really quickly. I'm doing A and B and then 87, 97. Okay, keep me honest, those of you guys that have questions, just in case I forget what you're asking me to do. Kyle, go hit escape on my keyboard real quick. I'm changing my mind. You guys can tell me what the directions are. You wrote them down in your homework, right? Hit escape real quick. Thanks. That's all I need. Oops. There we go. Okay, number 45. So when you guys pull out the T, some of you, you're like, oh, it was easy after that. And some of you are like, no, it's not. It's a quartic. But here's the dealio, kiddos. How many terms are there in this quartic? Are there 5? Are there as many as there could be? No. And specifically, what's really nice is this is a trinomial that I can totally factor only using t squareds. Now pause and think about it. If I only use t squareds, I know I'm using my cheater guess and check method, but check it. If I only use t squareds, am I going to have a t to the fourth term, yes or no? Yeah. Am I going to have an outer and inner making t squared terms? Yeah. And am I going to have a constant? Yes. I'm not scared if the polynomial has a degree and then half of that degree and then a constant. I'm never scared of that. If I ever get a trinomial with a degree, half a degree, and then a constant, I can always factor it using basically the modified x method of thinking through positive 9 and negative 6 and saying, hey, that's negative 3 and negative 3. Just instead of using t, I'm using t squared. When do things get messy? When I have a t cubed or a t? But if I have a power and a half a power, I'm great. I can do that trinomial just using the x method. Now, help me out. Letter A, were we just factoring? Were we finding zeros? What were we? Ah. So finding the zeros, do I have to set that equal to 0? Struggle. But couldn't I rewrite this to be t and t squared minus 3 squared? Ooh, I think I have some zeros with multiplicities. I'm going to have this guy equal to 0 and this guy equal to 0. This one, I just get 0. This one, we would actually need to do t squared minus 3 equals 0. T squared equals 3. Square root would be an absolute value, which means plus or minus 3. With the square root, that's good. Whew, I don't know the square root of 3. I mean, I kind of do, but Mrs. Leon knows it better. Anyway. And Mr. Che, I think they both have square root of some of the basic square roots memorized within 1, 2 decimal places. Anyway, maybe I should do that someday. What was letter B asking, though? Kim, you asked me for letter B also. Multiplicity. Going back to what Gavin said earlier today, and what a couple others of you answered when I asked. We're looking at the powers of the factors. So what's the power of this guy where the 0 came from? Just 1. So his multiplicity, just 1. But these guys, didn't they both come out of here? And didn't both of them have a squared? So therefore, both of them are going to have multiplicity of. So my graph is going to be bouncing those and crossing through at that one. And just kind of thinking about this guy, knowing his end behavior. and then putting on a graph my negative root 3, wherever that is, and my positive root 3, wherever that is. I could be like, well, I think it's going to do some sort of up thing and then cross down. Well, that doesn't work. He's supposed to be bouncing, right? Okay, well, hold on. That doesn't bounce. How can I bounce? 1, 2, 3. Is that legal? Bounce, bounce. But that's a lot of Humpty Dumptys going on, right? 1, 2, 3, 4, 5 is legal for a 5th degree polynomial. 1, 2, 3 is legal for a cubic. 1, 2, 3, 4 is legal for a quartic. Doesn't mean they're all like that. But that's up to how many turns they can have. This guy can have 1, 2, 3, 4 turns. Anyway, not that you have to be getting that graph, and not that that's a perfect graph. Just trying to give you an idea of the multiplicity. Multiplicity, if it's an even, we're bouncing. If it's an odd, we're crossing through. Okay, we did A, we did B. Robbie, does that get you kind of going on it? So then for C and D, oh, D is a graphing calculator. C is in your notes, but we also talked about how, hey, I think there might be 4 turns. Then we are going to number 87. Was that right, guys? Okay, 87, then 97. Number 87, while I'm taking a picture, what were the directions for this whole section? Okay. Oh, this is one of the big doozies, huh? Hey, what's really nice about this guy, though? It's already factored, so I already know my zeros are going to be positive 2 and negative 2, and both of them with a multiplicity of 2. Because they both have little squares. But hold on, the first thing we were supposed to be doing was the leading coefficient test, right? Leading coefficient test. If you were to FOIL this all out, can anyone tell what power the t term, which is going to technically have a negative 1/4 with a lot of stuff after it, what power is this guy going to be to? Good. So this is a 4th degree polynomial with all sorts of yucky stuff after it. And so a 4th degree, isn't that going to be an even? Is it up or down? Yeah. Down. So therefore, as x goes to negative infinity, where's my f of x going? Down. And as x goes to positive infinity, where's my f of x going? Down. So this guy's going a down and a down. Letter B said zeros. Didn't we already identify that? Oops. I'm calling them t's because that's what the problem called them. So negative 2 and positive 2 or plus minus 2. Letter C, is that our sufficient solution points? Is that the sign chart? Yeah. What intervals did you guys make? You guys should have already done these.
Negative 3, negative 1.
Oh, not the test point, sorry, the interval. So it would be negative infinity to negative 2 though, right?
Yeah.
And negative 2 to 2 and then 2 to infinity. And that's why I was hearing numbers like, hey, why don't you use negative 3? Good idea. 0? Anybody use 0? And then 3? When you plug and chug to F, what'd you get for negative 3? Yeah, negative 25/4. For 0? I don't think it's negative 4, is it? Because that'd be 4 and that'd be 4. And 4 times 4 is 16 and 16. Oh, negative 4. Yeah. I didn't do my mental math very well. I'm sorry. And then when you plug in 3, you ended up with negative 25/4 again. And then you were seeing, can I put all this information together to get a graph? We know there's a 0 at negative 2 and at 0. No, there's not one at 0. There's zeros at negative 2, positive 2. We tested what's going on at negative 3, and it was negative 8-ish, so it's down here somewhere. And at positive 3, it's negative 8-ish. Oh, that makes sense. This is going down and going down, right? But what was going on at 0? Negative 4-ish. So wait, does it cross through it all, guys? Why doesn't it cross through it all? It's going to go up and bounce and go down and go up and bounce. There he is. Dun, 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 approximately. So he's going to go up and bounce, has to go hit that guy, and then go up and bounce, and there we go. Then you guys are supposed to maybe plug it in your calculator and see how close, and that should have been pretty close. Gavin, what's up, bud? Oh, no. To be honest, I can look at the very beginning and say at most there will be 3. But until I think about the behavior of where it's coming from, because it's coming from down, and then eventually it has to end going down again. And I think about things like zeros and my points in between. I think about things like, oh, it has to bounce. There's a turn. And then, well, somehow it has to get back here, so it must turn to go back. Because remember, polynomials always make smooth turns. So when I hit this point and when I saw it had to go there, I was like, all right, fine. And then I knew that bounced both because of the multiplicities. But yeah, I just kind of think through each of my clues, and at the end I'm like, oh, I think it needs 3 turns. Or in the other one, I think it needs 4 turns. Just putting all the clues together. It's like a little detective. A little bit of sleuthing is necessary as far as the work that goes into it. Number 97 was the last question that you guys asked. The sad thing is I think my book spazzed out. Every now and then it doesn't like pages, like there's an error or in the coding there's something wrong. So let me go ahead, and as you guys get back into your notes, it's okay, keep your homework spirals out if you have a question on 97. Go fast, Kim. As you guys get ready for us to go into notes, let me go ahead and peek the old-fashioned way at what number 97 says. So the old-fashioned way, was 97 a word problem? Yeah. Was I cool like that? You guys noticed in your book, whenever something like the difference quotient came up, or something like that weird, what was it, 83, 85, 86, those weird problems with rectangles that we never really went over because I didn't require it for the test. Or something like IVT comes up. Do you see this really spiffy symbol that comes up in your book as well? Yeah. You guys should pay attention to that symbol. It's a symbol from calculus called an integral. It's basically saying, hey, this is going to be helpful later. Just in case you want to know what's going on in your book. Okay, number 97 says, here. What for number 97 it'd be a lot better because it's a hold up. Make that one tomorrow, and I'll get a picture for you. Sound good? Okay. Because with the book out, it's going to take a little too much time for me to make a picture right now. But I understand the struggle, and so I'll get a nice picture for that for tomorrow. All right, section 2 point what? 3. Okay, we were supposed to start 2.3 yesterday. We're going to bust through it today because I have full confidence that we can divide. So let's see if that confidence is well-placed or misplaced. How do we, using long division, prove that this and this are the exact same thing? We divide the first one and see if it ends up being the second one. So how do we divide? Who goes where whenever you're dividing a fraction? What goes in the box? The numerator or denominator? Yep. So I have x to the 4th. Ooh, let's see if you guys can remember starting right now. Why is there a 0? There's no x cubed term, but there could be. Pat in the back, especially if they're falling asleep. Real quick. Reach out. If not, give me a high five. Quick little soft. Okay, here we go. Top goes in the box. Numerator goes in. We divide numerator by denominator. We divide numerator by denominator, and I'm leaving the place. I'm leaving the place for an x cubed and an x just in case. Now, just like with any long division, we're looking at the larger terms and saying, how many times do you go into u? X squared times what is x to the 4th? I need an x squared. But I have a binomial chilling over here. I can't just do x squared times x squared is x to the 4th. What else do I need? But am I going to put the 5x squared right here? No, I'm going to line it up. Now in division, we guesstimate how many times the outer goes into the outer. Then we distribute for binomials or polynomials. We distribute because we multiply that by what's here. And in division, what operation do we do as we go down? Always subtraction. But why am I putting parentheses? And why am I going to make a big deal? So you don't kill seals. Distribute the negative n. And to be honest, what I would do if I were you and what you're going to see me do in class is I'm going to distribute right away and not try to do it in my head because I know myself that I make mistakes. So distribute. It's going to be plus a negative and a negative. I'm going to distribute the negative to both terms. Now I can just add down. X to the fourth minus x to the fourth. Got it. 0x cubed plus 0. Got it. 0. Negative 3x squared minus 5x squared is negative 8x squared. And I bring down everybody else just in case I need them. And I ask myself the question, okay, cool. How many times is x squared going to negative 8x squared? Negative 8. Careful. Negative 8 times x squared is negative 8x squared. So then I distribute my negative 8 to both terms. You guys see why I have a negative 40? Negative 8 times a positive 5. I'm going to say, watch out. I'm going to distribute my negative. Oh, they all turn positive. That's a 0. That's a 0. That's a 39. Does this prove or disprove that y1 equals y2? How does it prove it? There's a remainder. Oh, in math, we don't just write remainders anymore. That was like elementary stuff or middle school stuff. Now we say this is a fractional portion of that. So we can come up here and say that remainder means there's 39 pieces of x squared plus 5 left over. Dun, 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 dun. Check, we're done. But it also had us review long division. So quick reminder of long division. Not that you're going to have to memorize this per se. But there are a couple times in homework examples or problems where it's going to be useful to have a couple reminders of what happens when you divide. What happens when you divide? When you divide polynomials, first of all, you have some sort of numerator. It's not always written, though. Some sort of numerator, some sort of denominator. Some sort of numerator, some sort of denominator. We could call this one the divisor. You could call this answer the quotient, this answer the remainder. This is our original function. Remember, the goal is that we're having this nasty big ol', look it, a quartic, big ol' polynomial, and that's not even that bad. A nasty big old polynomial that we're trying to break down. So we have a function f that we're trying to break down by dividing by factors or possible factors. So we put the numerator inside, denominator outside. We're trying to figure out, hey, what's left over? We're going to have some sort of quotient, but we might have a remainder also. But if we do solve this problem, if we do get these as answers, here's what's going on. We could rewrite this f guy, we could rewrite him broken down as d times q, q times d, as far as x squared minus 8 times x squared plus 5 could have been that original polynomial, but not perfectly. There's a remainder, so we'd have to add and say, okay, if we were to multiply these two together, we'd just have to add r, and then we'd have it. Or another way of writing it is that we could say f divided by d is q times plus the remainder over d, which is technically just math, dividing everybody by d. But anyway, that's just a little bit of notation. I want you guys to bust out this long division problem. Some of you might be like, it's the sum of perfect cubes. It is. And there actually is a formula that you could memorize out there, kind of like difference of squares and perfect squares. The problem is, almost no one ever remembers it, number one. And number two, long division will get you it every time without having to memorize something else. And as soon as you go to a quartic or a quintic, that formula wouldn't work anyway. So instead of memorizing some formula for this, we're going to actually use long division and say, I think x plus 5 goes in, and it does. Kyle, go ahead. I'm just having you review the long division first. Kyle's like, but is there a thing called synthetic? Yeah. But just a quick heads up. The first example we did, synthetic couldn't have been used. Had an X. But this one has an X to the 1. We could use synthetic on this one. But we're going to review long division first. And I know the directions are up above, like on the ceiling almost. But technically the directions do say use long division to divide. Yes. Oh, there's synthetic. If you guys finish dividing, some of you might finish really quickly. You go ahead and remind yourself of the steps to synthetic. You could remind yourselves and take some notes on the steps to synthetic and then go back and check that you were right with synthetic. Or you could FOIL, I suppose. Or I should say polynomial multiplication. I'm going to start playing, but you guys keep doing what you're doing. Hopefully you're already well on your way to an answer. Anybody else get a remainder of 0? Ooh. So I could say and the cool thing is this division problem is leading up to section 2.5 where we could say, hey, if we needed to factor this guy, he could just be x plus 5 times x squared minus 5x. And maybe we could even keep going. Those are the two different ways that we could write this answer. And both of them show us different things. Synthetic division says, hey, there's another way to do this division if and only if I'm dividing by a linear pair. If and only if I'm dividing by a linear factor. Ways I'm going to talk about the linear factor. One is going to be the actual factor itself, x minus a, and the other is going to be about its 0, which is x equals a. In synthetic division, it's really helpful. To know the terminology. X minus a is the linear factor that we're dividing by. X equals a is the 0 of that factor. So there's a shortcut. Anytime legal here as well. That's a linear factor. Hey, we can use synthetic. And how does synthetic work? As you guys are writing down the steps, or some of you have already written them down and you're just kind of sitting and staring and pondering, let's go through them. We're going to set up the problem, set up our synthetic division, which has a division line, and it has a box. And we're going to go ahead and steal our polynomial's coefficients. So we have 6, we have 7. If there were any zeros, we'd have to use them as well. We're going to put the 0 of the factor in the box. So what's the 0 of this guy? X equals 3. So I'm going to put 3 in the box. Because I found the 0, I'm going to do addition. I'm not doing x minus 3. X equals positive 3. So I've already kind of flipped the sign. I'm going to use addition for all of synthetic. The multiply add pattern says first carry down the first coefficient, which is 6. So carry down the first, and then multiply add says multiply box times number 18. Rewrite and then add. 7 and 18 is 25. 3 and 25 is 75. 74. 3 and 74. It's going to end up being 232. Double checking. 12, carry the 1, 21, and 22. Oh, 222. I apologize. 222. Here's the crazy thing. Every time you divide a polynomial by a linear factor, the degree always goes down 1. So where it had 4 terms originally, now it only has 3 terms. I'll show you why in just a second. But this last term is still important. But it's going to be the remainder. So I could rewrite without doing any long division. The answer to this division problem will be 6 with a degree lower than the original, 6x squared. And then we count down from there. The next term would be then an x term. The next term would just be a constant. And why am I writing a division bar for the remainder? 248 over the original linear factor of x minus 3. What would have happened if you had done long division? Same exact thing. What would happen if we went over here and tried to check synthetic division? Same exact thing would result. What are your guys' objectives for tonight in this homework? Oh, we already did that example. I just squished it on the page before. To practice. Let's see, what do we got? What did we not get to? Okay, we didn't get to 2 homework helps, but let's just stop on this last page. We didn't get to 2 homework helps, but I think we're okay without homework helps. This is honors, and you guys have the book. What we didn't get to was the last application of division. So far, we've just said division is going to be helpful for factoring. What we didn't get to talk about, the last application, is that when you divide the remainder, and if I were you, I would just make a point. The remainder, or r, is going to be the same thing as the function value at a. The remainder, or r, is going to be the same thing as the function value at a. So we could just plug in 1 to something like this example. And we would go ahead and get 2 minus 7 is negative 5 plus 3 is negative 2. But here's the dealio. If you were to have done synthetic division, you can go ahead and pack up, with the 0 in the box and with each of your terms written out, guess what would have also been the remainder? These will always match. So you could plug in to see what the remainder will be, or you could find the remainder and see what the plug-in would have been. Check it out in homework tonight. Let's see how you do. Still due tomorrow by 7 a.m. You missed a couple homework helps. Go ahead and start clearing out. Look at the examples in the book. You guys got this. Divide, divide, divide.
Sent us a message and told you to get the